Good afternoon, everyone. I'm Sherjeel. I'm a senior scientist at Silicon Austria Lab. We are a research institute based in Austria. And this work was done in collaboration with FH University in Carinthia, Austria, and funded by FFG in the bridge call. So today I'll talk about I'll talk about tactile sensors and how some aspects of it we have improved. So just a general introduction to tactile sensors. We know in the field of flexible electronics, they are targeted towards improving interactions between humans and machines. So more specifically in applications such as wearable health monitors, soft robotics, and prosthetics. We do have commercial tactile sensors that work fairly well, but they are not tuned for applications that we are targeting along the lines of flexible electronics. Also, there is a lot of literature. This is a hot topic. So in literature, you can find many research works on this topic. But most of the time, we see that they use complex fabrication approaches. Their performance will always be good, right? This is the idea. They will show good performance, but we want to bridge the gap between this research and industry so that printed electronics can become more proliferant. And also, of course, we have state-of-the-art tactile skins, which offer very high performance, but again, at the cost of complex fabrication approaches and less practicality in integration with electronics. So we present two things. One is showing a scalable, low-cost additive manufacturing method to make our textile skin. So it will be mostly based on screen printing. Second, a point that I saw less addressed in the literature was the crosstalk between the sensors. When you move towards more practical the applications, these are some of the aspects that we have to focus on. When you have an array of sensors, as we see in all of these works in tactile sensing, then there is a lot of crosstalk between the sensors and noise from the environment. Just quickly going over the basic sensing principle, it's a parallel plate capacitive sensor. One plate is moving and there's a dielectric medium. As the distance is increasing, our capacitance increases. So in our case, we have a simple design. At bottom layer, we have our sensor. There is a compressible layer in the form of a polymer. So we use PDMS, EcoFlex. It depends upon the application. You can change the compressible polymer. And on top, we have another layer of printed metal on TPU. And as you press on the individual sensor node, the gap between the two plates changes, and hence force is shown as a change in capacitance. So our sensor was designed based on screen printing. So the metal layers were printed on a TPU. The white background is the TPU layer, and the silver is our printed metal layer, screen printed. And we have made an array approach matrix. So four rows, each having 4 sensors. And on top of it, we deposited our dielectric compressible polymer, which is the dielectric. So the metal layers are with the silver ink, and this ink is stretchable and flexible, so it's suitable for tactile sensing, and it's very robust. We have tested it immensely, and the dielectric is polymer. It was EcoFlex in this case, but it can be different ones, and we use blade coating to spread the polymer on the surface because we want a homogeneous surface so that the uniformity across the whole array is good. So as you see, there are multiple sensors here. So there would be crosstalk between each. If you apply a force here, often you will see the force is also shown in different, because of the fringing field, it couples with the substrate. If you see a fringing field of a parallel plate capacitive sensor is not just between the two plates, it goes around the surface too. It's weaker, but is there. So the idea was, and this idea is coming from conventional PCB technologies. When commercial touch sensors, these techniques are commonly used. So we wanted to imitate those in a soft form. So basically what you want to do is by introducing a shielding electrode, you want to limit this fringing field area so as to reduce the effective area where your noise sources can come in. So I'll go to the results later on, but just to complete the sensor stack, so we need a top layer. So we had a top layer with again 16 sensors, and here you see we will have 4 columns and 4 rows. And the way we have flipped it 90 degrees is that the overlapping area is only on the sensor, not on the interconnects. Because if your interconnects have overlapping areas, then also they become a parasitic capacitor. Another thing is that on the bottom layer, we have a larger area shielded shielded layer, and on the top we have a smaller in the form of lines. Here we just want to demonstrate that you can tune the size of the shielding layer to save the material according to the application. So it's a balance between the shielding layer area and the sensitivity, because adding the shielding layer will reduce the sensitivity of every good thing comes at a cost. It's just an overview of how our dielectric is looking like. And then going to experimental setup, we did a normal force testing using a Zwick benchtop machine. And then we used a robot, U10 robot, to do more multi-point testing. And it was connected to IoT-based electronics for real-time data manipulation and viewing. So coming to the results, so first, on the left, we can see the effectiveness of the shielding. So in the red area, the shielding electrode was not connected to the ground. So any movement of conductive objects or dielectric objects like hand in the vicinity of the sensor causes a large drop in capacitance, which is because we affect the fringing field and hence reduce the capacitance. Then the moment we connect our shielding layer to the ground, we do see a drop in capacitance because I am sinking a lot of the fringing field that results in the capacitance. However, movements we reduce the sensitivity to and the baseline value. However, any movement of any objects along from the 6 second to 10 second mark, we don't see a change, not considerable, as we said before. Around 10 and 11, we really went down to 1 millimeter distance and moved object in that area, and we do see some changes because, again, it's not 100%. It essentially reduces this area where you are affected by noise. Then we wanted to show more versatility, so we did some tests with machine learning. First, we did a moving average of 4 and RMC test. So basically, this shows that it shows the reduction in the noise in the data and helps us analyze the underlying trends. And it identifies consistency and reliability of our readings. Then we did linear regression to correlate our RMC values. So it helps us quantify a relationship between sensor capacitance and the reading. And this mathematical model can help us predict force based on sensor data for real-time applications. So just going quickly over some of the applications that we can see for such tactile sensing. Enhanced tactile sensing for delicate grasping in robots. So robots have more feeling of what objects they're grabbing. Help people with using prosthetics to give them a sense of feeling with the objects they interact with. And also to create a more digital interaction between humans and machines for different applications such as VR. So in essence, we're showing a scalable, low-cost manufacturing method. So this tactile sensing is a common concept that has been studied in details. We have high-performance systems too, as I mentioned, but our idea was to show a more scalable and low-cost manufacturing technique. Also, we wanted to address and largely ignore topic of crosstalk between sensors, especially in a matrix approach, and show the method of EMI shielding that can be implemented. Limitations of the current work is, of course, this trade-off in the sensor sensitivity due to addition of the shielding effect. Some feature improvements that we see are enhancing the sensitivity without compromising the EMI shielding, integrating more advanced machine learning techniques for better performance, refining our fabrication process, and exploring new applications. So, thank you for your attention.